In this video, we'll complete our description of the contrastive divergence algorithm as applied to a restricted Boltzmann machine and get an actual concrete parameter update rule. In the previous video, we've talked about how to estimate the negative log probability gradient, we needed to estimate this double expectation over both x and h in the model. And then this justified, because this is actually intractable to compute, this justified an approximation. And in contrastive divergence, the idea is to replace this expectation by a point estimate where we'll actually just sample a single value for x. And to obtain that value of x, which we'll call x tilde, we actually perform a few steps of Gibbs sampling initialized at the current training observation. So now let's look at how we can, in the context of a restricted Boltzmann machine, compute this full update, assuming that we've performed a few steps of Gibbs sampling starting at the current training example xt. Okay, we need to perform a few more derivations to get the full algorithm. So remember that we have to perform an expectation over h of the partial derivative of the energy with respect to any parameter. So let's do first the partial derivative of the energy with respect to any parameter. So actually we'll just do the case for the connection between the jth hidden unit and the kth input. So the partial derivative of the energy with respect to a connection is thus the partial derivative of this. That's just the energy function. And we notice that there's only one term which involves this particular connection between hj and xk. So really, to be strictly correct, I should have j prime and k prime, but just to simplify, I'm using the same indices. But you should understand what's going on here. So really, this whole sum here, in particular this sum here, is the only one that involves connections. So the partial derivative with respect to this or that is 0. And then the only term here that involves exactly the same connection between hj and xk is the one that involves hj and xk. So the partial derivative of that here is really the partial derivative of the term wjk times hj xk for the same value of j and k. And this is a term that's linear in my parameter. So its value is just whatever was multiplying that weight, which is hj and xk. And then I get the minus, which was here. And so if I want to put that into matrix form, so to get the gradient of the energy with respect to the full matrix W, then you should be able to see that this is just minus the outer product of the h vector with the transpose, so with the x vectors. Or in other words, the matrix product between the column vector minus the column vector h times the row vector x. Now if we perform the expectation with respect to h, condition on any value of the vector x, so we have this, we're trying to do this for theta equals to a connection. So we've shown that this is equal to that here, minus hj times xk. So this is an expectation over all neurons in the hidden layer H, but this involves only one hidden neuron, the jth hidden neuron. So really this is just a sum over that neuron being equal to 0, 1 of the term that we have here, but weighted by the probability that hj is equal to its given value. And I'll notice that in this sum there's two cases, hj equals to 0, hj equals to 0, hj equals to 1. If hj is 0, then this is 0, and otherwise this term is just that, equals to 1. And so that's the only non-zero term, so really this sum is just equivalent to minus xk times the probability that hj is equal to 1 given x, which is given right here. And again, if we want to write this into matrix form, then we notice again that we could write this as the outer product of minus a vector, which I'm going to call h of x, which is the vector that contains the probability of each hidden unit being equal to 1 given x. So I put that into vector, and notice that this is just the sigmoid of the bias vector plus the matrix of weights w times x. So I take that vector h of x, and I do the outer product with the vector x. And so the entry in that matrix at row j and column k is going to be exactly this. So notice also that conveniently h of x is actually just the value of hidden layer in a feed-forward neural network with sigmoidal activation function. This is somewhat of a coincidence, but we start seeing that this is really a neural network. There are relationships between the restricted Boltzmann machine and neural networks. And so if we put everything together, it means that if for a given training example and a negative sample that I've sampled with k steps of Gibbs sampling initialized at xt, so I'm calling that x tilde, then if I want to update W, my matrix of connections, then I want to take W minus some learning rate of an estimator of the gradient of the negative log probability of the observed training sample. We've seen that this expression was the difference between a positive phase and a negative phase. The positive phase is an expectation condition on the observation, and the other one is an expectation where I'm also taking the expectation over the x vector. Then I've argued that I can compute this exactly. So what I'll do is that I'll replace this double expectation with a point estimate where I'm going to sample a value for x, which I'm calling x tilde. And then given x tilde, I can actually do the remaining part of the expectation over h. And then I've shown that for any value of x, this expectation would correspond to my h of x vector, but for xt, because I'm conditioning on xt here, multiplied by the transpose of xt, and then this, which has the same form, but instead I'm conditioning on x tilde, that's going to be h tilde times the transpose of x tilde. So I combine that together and multiply this by alpha, and then I can just increment w by that. Okay, so notice we had a minus here and a minus there, so that's why there's no minus here anymore. We have a plus here, and then we have a minus here. So to sum up, the pseudocode for contrastive divergence corresponds to going over the training examples. For the current training example, perform k steps of Gibbs sampling to obtain a negative sample x tilde, and then I update my parameter, so I have the update for the matrix W. I'll leave it as an exercise to show that we get a similar update for B and C. So it's going to be what is observed minus what I've sampled. So for the C vector, which is the bias for x, I get a term that involves x. And for the B vector, which is a bias for the hidden units, then I get the vector of probabilities as given condition on either xt or x tilde. And then I keep doing this until some stopping criterion. So for instance, if until my parameters don't change too much, or for a fixed number of parameter which I could cross-validate somehow using some given criteria of generalization. So this is so the acronym we use for contrastive divergence is CD, and sometimes you'll see CD-K where I explicitly illustrate what's the value of K. So the number of Gibbs sampling steps. The bigger K is, the less biased our estimate of the gradient is going to be. So if K was very, very large, then it means that my Gibbs chain would have essentially converged to the true model distribution. And so I just get a Monte Carlo estimate of the expectation. So in other words, in expectation, this estimate would correspond to the true expectation. And now the less K is big, however, the less it's going to be, the more bias there's going to be in my estimate of the negative log likelihood gradient. However, it turns out that to extract some features or to initialize neural networks, which we call pre-training, which is something we'll discuss later in this course, k equals 1 works well in practice. And so there's been some research for trying to understand why that is. The initial paper on contrastive divergence was trying to argue that this actually makes sense, and And so we'll just live with the fact that, and we're actually quite happy with this, that k equals 1, so performing just one sample of h and then immediately resampling x stilled actually provides is a good procedure for getting a meaningful value for x stilled in order to learn a good value of hidden units, at least in terms of extracting features. However, if we were to look at how good the model is, and it turns out that using larger values of k is actually beneficial. That is, if we look at whether the value of the average negative log probability of a test set, for instance, if k becomes bigger, then typically this will be much better. But in terms of just extracting features, that is getting a good value of the vector h of x, which we could then use as a feature representation for another learning algorithm, it turns out that k equals 1 works well in practice. All right, so that summarizes the contrastive divergence algorithm.